I wanted to do a little bit more from section 8.1. So in this section, we're looking at the distribution of the sample mean. And in the last video, we looked at a demonstration, pretty much just kind of showing where these two properties come from. So the two things to know are the mean of the sample means is the same as the population mean, and the standard deviation of the sample means is where you take the population standard deviation divided by the square root of the sample size. Okay, so let's take a look at an example of this now. Problem 5, it says the upper leg length of 20 to 29-year-old males is normally distributed with a mean length of 43.7 centimeters and a standard deviation of 4.2 centimeters. Let the random variable x represent the upper leg length of a 20 to 29-year-old male. Okay, part A, what is the probability that a randomly selected 20 to 29-year-old male has an upper leg length that is less than 40 centimeters? Well, this is only one individual selected, so the way that this problem is going to go is just finding a normal probability like we did in Chapter 7. X represents the upper leg length of a 20 to 29-year-old male. So I want to find the probability that that length is some number less than 40 centimeters. First thing you got to do is change the variable from x to z using the formula for a z-score. Okay, so take x minus mu over sigma to get your z-score. Do that also with the actual numbers. 40 minus the mean is 43.7 divided by the standard deviation, that's 4.2, and we get a z-score of negative 0.88. Then you'll go to the chart. So here's negative 0.88. I'm getting 0.1894 is the area to the left of that number, and that's what you see here. Okay, so if we were to look at all the males in this age group and randomly select one of them, there would be an 18.94% chance that the upper leg length of that person is going to be some number less than 40 centimeters. Okay, nothing new here. This problem could have been right in Chapter 7. Okay, let's take a look at Part B. A random sample of 9 males who are 20 to 29 years old is obtained. What is the probability that the mean upper leg length is less than 40 centimeters? Okay, now this problem is different from the last one because in the last one we only selected one individual. Now we are selecting 9 individuals. Since 9 individuals are selected, this is going to be finding a normal probability as we did in Chapter 7, but we need to use the standard error as our standard deviation when we change the variable. Okay, now remember, the mean of the sample means is the same as the population mean, so mu sub x bar is the same as mu. Sigma sub x bar is where you take sigma divided by the square root of n. Sigma is 4.2 for this problem, and n is 9, square root of 9 is 3. If you take 4.2 divided by 3, you should get 1.4, and that's an exact. Okay, that's sigma sub x bar. So that's not a whole lot of spread in the sample means. We can see this is a small number. Now, I want to find the probability that the sample mean of these 9 numbers is going to be something less than 40 centimeters. I'm going to change the variable from x bar to a z-score. Take x bar minus mu sub x bar over sigma sub x bar to get your z-score. X bar is 40, and I'm going to subtract mu sub x bar is the same as mu, that's 43.7, divided by sigma sub x bar, we just found that number is 1.4, and we get a z-score that is negative 2.64. So then I'm going to go to the chart here. Negative 2.64, the area to the left is 0.0041. Okay. So the interpretation here would be to say that, if we were to select 9 males of this age group randomly, and compute the upper leg length for each one, and then find the mean of those 9 numbers, there would be a 0.41% chance that the mean of those 9 numbers is going to be something less than 40 centimeters. So that would be very unusual for the sample mean of these 9 numbers to be less than 40 centimeters. Okay, this is a very small probability. Now, just an observation here, the population mean is 43.7, right? So if we're randomly selecting numbers like asking for the mean to be less than 40 when most of the data is going to be around 43.7, that's probably going to be a hard thing to do. Okay, so yes, that would be very unusual. Part C, what is the probability that a random sample of 12 males who are 20 to 29 years old results in a mean upper leg length that is less than 40 centimeters? Okay, so this is going to be similar to what we did in Part B. Since there are 12 individuals that are selected, we're going to be finding a normal probability like we did in Chapter 7, but we got to first compute the standard error. The mean of the sample means is the same as the population mean, so mu sub x bar is going to be the same, 43.7 as what mu was there. And sigma sub x bar, I got to take sigma divided by the square root of n. N in this problem is 12, and if you go to the calculator and type in 4.2 divided by the square root of 12, I was getting roughly about 1.21 if I go nearest 2 digits on that. Okay, now we want to find the probability that the sample mean of these 12 individuals is some number less than 40 centimeters. Again, we got to change the variable to get our z-score. So I'm going to say x bar minus mu sub x bar over sigma sub x bar to get my z-score. By the way, notice how I'm not writing z bar. I'm just writing z, because I need to get my z-score and I need to go to the chart to look up my area to the left. I'm not taking an average of z-scores. I'm taking an average of x values, but I am not taking an average of z-scores. Okay, so just a notational thing there to point out. When you change the variable here, take 40 minus 43.7 is mu sub x bar divided by the standard error, that's 1.21, and we get a z-score of negative 3.06. Go to the chart, we're talking about area to the left. Area to the left of negative 3.06 is 0.0011, and that's what I'm getting there. Okay. Again, it would be very unlikely for the sample mean of these 12 individuals to be some number that is less than 40 centimeters. We have less than a 0.11% chance of that occurring. That's probably not going to happen. Part D, what effect does increasing the sample size have on the probability? So when you compare these two calculations, B and C, the probability got smaller when you increased the sample size. It says here, the larger the sample size, the less likely it is that the mean upper leg length is less than 40 centimeters. This is because of the smaller standard deviation that is sigma sub x bar. Okay, now, by the way, I think this should make total sense to us why this probability would be smaller. I've already mentioned that, the mean is 43.7. So most of the numbers are going to be around 43.7. We don't have a huge spread in the values, although there is a spread, okay, but most of the numbers are going to be around 43.7. Now, we need 12 numbers to be selected, and when we compute the mean of those 12, we need it to be some number less than 40. Well, that's probably going to be hard to do if most of the numbers are going to be around 43.7. It was already hard to do when we only selected 9 numbers, but now if you're going to select 3 more numbers, well, the three more numbers have to be less than 40. That's hard to do if most of the data is around 43.7. Okay, so again, this would be very unusual. Let's take a look at Part E. It says a random sample of 15 males who are 20 to 29 years old results in a mean upper leg length of 46 centimeters. Do you find this result unusual? Okay, well, let's find the probability that the sample mean would be some number that is 46 centimeters or more, and then we can state whether that would be unusual based on our number. Since 15 males are selected, this is going to be finding a normal probability like we did in Chapter 7, although we'll need to get the standard error. By the way, the mistake that I will see students make is that they'll be using sigma and not sigma sub x bar when they change the variable, and that will lead to a wrong answer. Okay, so be careful about that. Mu is the same as mu sub x bar. Sigma sub x bar is not the same as sigma, so you got to take sigma divided by the square root of n. 4.2 divided by the square root of 15 is roughly about 1.08. And so I've already got this set up here. I'm going to change the variable. And that allows me to get my z-score. And 46 minus 43.7 divided by 1.08 is roughly 2.13 if you go nearest two digits. We're looking for the area to the right of that number. Table only gives area to the left, so I'll need to use the complement rule. Switch the sign, of course. And so that would indicate that you're describing area to the left. Now you can go to the chart and look up that area to the left of 2.13. Area to the left of 2.13, I'm getting 0.9834. And subtract that number from 1, and we get 0.0166 as the probability here. So the interpretation would be to say that if we were to randomly select 15 males in this age group and compute the mean upper leg length of those 15 males, we have a 1.66% chance that the mean of those 15 individuals would be some number that is 46 centimeters or bigger. Okay, so if that were to happen, yeah, that would be very unusual. Okay, this is a very low probability. Again, most of the numbers are going to be around 43.7. So asking for 15 numbers to produce a sample mean that is more than 43.7 is likely not to happen. Okay. Now there's a note. In the demonstration for serum sodium levels that I had shown in the previous video, we were assuming that the original population was in fact normal itself. By the way, we were also under the assumption here that in this problem we have something that is also normally distributed, okay, in problem 5. With this assumption, we saw that the distribution of the sample means was also normal. Okay, I had shown you 3 histograms, and all 3 of those histograms had a normal curve overlaid on top, indicating that that it was still, bell-shaped and symmetric. Now, what if the original population is not normal? What would the distribution of the sample means look like? Okay, so in the next video, I'm going to show you another demonstration.